Okay, so thanks. So the next talk is by Dhrubaditya Mitra, who will be speaking on charged particles in MHD.
Thank you. Thanks. Hi, Sharanna, how are you?
Good. How are you doing?
Fine. Lots of old friends. That's always the fun of the pencil code meeting. So let me start trying to share my screen.
You can lower your hand.
I should lower my hand. Absolutely. Thank you. How do I do that?
I can try.
Reactions. There should be reactions. Yes.
And then lower hand.
Yeah.
Yes. I hope I managed to do that.
Yeah. Yeah, just share your screen.
Yes. So share my screen.
He's co-host, right?
He's a co-host. Yeah.
Okay. Can you see my screen?
Yes. Yeah. Make it full screen. Yeah.
I am going to.
Yeah. Good.
Right. So let's see. Okay. So thanks very much. So Piali asked me to talk about this, something that is somewhat old. This is something that I'm calling energization by reconnection. What we did is somewhat old, but the problem remains relevant very much, particularly so now. And it is good that I'm talking about it to Bangalore because this was done actually with people in Pune. Maybe some people from Pune are still attending this. I don't know. It'll be fun. So I guess everyone knows about charged particle acceleration. I'm mostly talking to astrophysics people, right? Are there anyone here who doesn't call himself, herself an astrophysicist? No? Okay. So let me see how to proceed. Somehow the slides don't move. Okay, now they do. Okay, so the important question, one of the most important questions in astrophysics, as you know, is the cosmic ray problem. By the way, stop me at any moment and ask questions. Feel free to interrupt me. So one of the most important ones are cosmic rays. And how do they become as energetic as they do? And what is their spatial distribution and so on? So this has, of course, this is a large part of astrophysics. And now one of the consensus being that the energization of cosmic rays are closely connected to supernovae. At the same time, the magnetic fields are supposed to play important roles. So there are two kinds of energizations that are important. One is what they call energization in shocks, and I'm not going to talk about it so much, but my interest is to understand how reconnection gives rise to fast particles. So I guess everyone knows what reconnection is. You have magnetic field lines, and if you think about your problem in a completely non-viscous, non-dissipative situation, then the topology of the magnetic field lines will remain always the same. However twisted they become, or whatever happens to them, their topology will remain the same. However, we know that the magnetic field lines can also reconnect. And this is what Parker used in his idea of how the coronal magnetic fields are, how the corona is actually heated. So that connects us to other most fundamental problem in astrophysics, the coronal heating problem. The corona is much warmer than the convection zone. So how does it get heated? And the Parker's idea was that it actually gets heated by lots of small reconnections. And each of these reconnections are supposed to give rise to slightly more energetic particles. So I will now be somewhat more pedantic and define exactly what I mean by energetic particles. So what I mean by energetic particles are fast electrons. So of course, what do I mean by fast electrons? There is an analogy between magnetic reconnection and a phenomena in fluids called vortex reconnection. So as you may know, that the equation obeyed by the magnetic field and the equation obeyed by the vorticity are the same if you ignore dissipation and if you are not considering density fluctuations. So in fluid mechanics, for example, there is this problem of vortex reconnection where vorticity fields, vorticity lines reconnect. And such a reconnection is because of viscosity. And you assume that that will give rise to some energization in the sense that some heat will be produced. But at the same time, you expect that the particles locally are going to have a Maxwellian distribution. You may get a slightly higher temperature, but it is still a thermal distribution. Whereas in the case of charged particle, what you expect is something fundamentally different. What you expect is the charged particle to have a non-thermal behavior. And that's typically what is meant by fast particles. So these are connected to what are called type 3 solar bursts, which are fast electrons presumably generated by reconfiguration of unstable coronal magnetic field. And in this picture you see, this is from a review of 2014. Typically, the signal from radio waves are in the sun is plotted in the following way. There is frequency on the vertical axis and time on the horizontal axis. And you can see that there is a signal which seems to be almost propagating in time, and it is also shifting in frequency. So these kind of plots are typical sign of what are called type 3 solar bursts. And that was the limit of detection in 2014. Now the Pune group of Divya Oberoi has gone much further, and they can actually detect signals much smaller than type 3 solar bursts. And I believe this is a very significant, this will have very significant role to play in understanding this phenomena. So you should look it up. This first electron beam then essentially slows down because the background plasma is cooler. And this gives rise to Langmuir waves. So this is the phenomena that will show up in the radio wave, and that is something we would eventually like to understand. Sharana, how much time do I have?
I think you started at 12:10 local time.
So it's just 6 minutes.
Huh?
6 minutes into your talk.
Yeah, you are just 6 minutes into your talk.
Okay, good that I don't have just 6 minutes.
Oh, no.
Thank you. Okay, so then it gives me some time to talk about fundamentals. So I guess for the moment, let me address myself to the students. So I believe you are reading Arnab's book, and you have all read Arnab's book very well. I can highly recommend it. So that has a chapter on energization of magnetic charged particles. And there he talks about the idea of magnetic mirrors. So you have a concentration of magnetic fields and another concentration of magnetic fields, let's say 2 magnetic clouds, and a charged particle can get reflected between one to the other. This was an original idea due to Fermi. And the idea is that as the 2 magnetic clouds move towards each other, the particle is bouncing back and forth, can keep gaining energy, and that's how it can get to very high energies. So there is a connection. You can kind of, the picture you can map to the following problem, that there is a ball which is bouncing between 2 walls, and one wall, which you can see in this middle picture here, there is a ball. Ignore gravity. One side is fixed, the other wall is moving, and this ball is bouncing between the walls. And you can imagine it's also like a child on a swing. So think of a swing. Now, if you give the force at just the right time, the amplitude of the swing can keep on increasing. Okay. So this, now stop a little and think in a more mathematical way. So the problem you are dealing with is actually a Hamiltonian system, because charged particle electrons in a magnetic field is a Hamiltonian system. But your magnetic field is changing by small amounts. So it is like an adiabatic perturbation to a Hamiltonian system. Okay. So this falls into the class of what are also called Fermi-Ulam problem. And this is actually one of the earliest problems to be simulated in a computer. In 1961, Ulam, who is a very well-known mathematician, and few other people actually coded this problem to a computer. And they found out that it doesn't work. So for the energization to work, one important thing is that the energy should grow exponentially fast in time. What they found out is, although in principle this could have been possible, for a particle that is bouncing between two walls and where the wall is moving with time, you can only get an energy which is algebraically fast in time, not exponentially fast. This was very surprising when it first appeared, and this got connected later to the developments of dynamical systems idea. So where some things people like Arnold and Kolmogorov showed that this is true because the Hamiltonian system, which can be think in terms of torides, is actually extremely stable to perturbations. That's why you get a only algebraic growth, not an exponential one. Interestingly, what was later found out is that if the time dependence of the wall is not smooth in time, but it can move and suddenly stop and suddenly move, then you can get an exponential acceleration. This was generalized to a connected problem of billiards. So over here on the left, you can see a billiard problem. There is kind of a stadium and there is a ball that is bouncing inside. All the reflections conserves energy. And then you can see the billiard slowly changes in time. Okay, it squeezes and expands. And the question is the same, can I still get exponential acceleration? This has been studied a lot. And what is known is that you can get exponential acceleration only if the topology of the billiard changes, as you see here. On the right, you see it's also a billiard problem where the surface changes, but some point it disconnects, it breaks up into two domains, and then some point it comes back again. So the topological change are extremely important for fast energization. Okay, now to the next step. So the magnetic reconnection problem, as you know, are two opposing magnetic field lines that are pushed towards each other by a flow. This is what is called the Sweet-Parker behavior. And then the field connects because of resistivity. And the one quantity that determines it is the so-called Lundquist number, which is the Alfvén velocity multiplied by the thickness, that's the distance between the two fields, divided by the magnetic diffusivity. Now, Parker and Sweet and Parker showed that you will get a growth rate which is proportional to 1 over the square root of Lundquist number. That basically means, you see, in the limit of magnetic diffusivity going to 0, Lundquist number goes to infinity, and your growth rate, the reconnection rate, actually goes to 0. This is slow magnetic reconnection. So if you had a reconnection which proceeded in the following way, in this way, it would be completely irrelevant in astrophysics, because in astrophysics, the magnetic diffusivity is normally extremely low. So what you need to have is a rate of reconnection which is independent of the magnetic diffusivity. So that's the other problem that has plagued us. About this, there is a very interesting theoretical model that has been studied, but this is a paper by Moffat and Hunt in 2002. Surprisingly, the paper, was there a question? Comment? No. Surprisingly, the paper has, I think it has 7, 8 citations. Almost no one has really paid it much attention. So here they show is that in a Sweet-Parker-like problem, that the reconnection rate goes to zero as diffusivity goes to zero. But if you have turbulence, then that is supposed to save the day. Okay. So you see, one of my friends are very fond of saying that the number of times turbulence is mentioned in an astrophysics problem is our measure of ignorance of that problem. We have a tendency of saying, oh, we don't understand this, then turbulence must come and fix it somehow. So the turbulence can give rise to fast reconnection. That has been speculated and then said many times. There is a Lazarian and Vishnika paper from 1999 that you should look at. And there is a paper which also include INC in 2011. But what I'm going to mostly talk about is a Luodio of 2009 paper. I don't know if Pallavi is here or not.
No.
Pallavi Bhatt, who is in,
No.
I think, ICTS now. So she is one of the experts in this. So here, what they calculate is that they have the magnetic field. They try to look at a magnetic field that has a sharp gradient, and then try to see how fast the reconnection work as you change turbulence in the problem. Okay. So you see here, they are plotting, for example, the reconnection rate as a function of the Lundquist number. And the black squares are the case where they have zero turbulence. You see the Sweet-Parker behavior of 1 over square root of S. The reconnection rate decreases as the Lundquist number increases. But as you go to add more and more turbulence, the reconnection rate actually follows a different pattern. And you see in the green one, for example, the reconnection rate is almost a constant. Okay. The epsilon here is a measure of the turbulent energy into the system, so to say. Okay. So the question now is that whether this can generate what are called suprathermal particles, which are particles whose energy is very much in excess to their general thermal background. So let me come back to the specific of the simulations that we run. So the first is, this is a usual MHD. The magnetic field equation, the velocity equation, the density equation, and the equation for instead of the magnetic field, the vector potential. But as this is the pencil code meeting, everyone is familiar with the vector potential. Now, one important thing is to have an initial magnetic field or an initial vector potential that has a pattern like this over here, cosine hyperbolic square x by delta, where delta is a small thickness. Now, this is weakly compressible force turbulence. And you see the way this is being done is that there is essentially a magnetic forcing into the problem. A magnetic forcing that essentially tries to replenish what is lost because of dissipation. So this is, you see, eta and then a negative sign, which basically means there is a positive viscosity, positive magnetic diffusivity term of the same amount as the magnetic diffusivity. So this is how this thing is being forced. At the same time, we solve for particles, charged particles. So x dot is V, and V is Q by M, E plus V cross B. Okay. So don't worry about the deltas. They essentially mean that you interpolate between the particles to the fields. You are solving for the fields in an Eulerian way, and you are solving for the particles in a Lagrangian way. So to find out the fields at the position of the particles, and the particles can generally be off the grid, then you need to interpolate. Now, of course, the particles that are moving are also going to generate, fast moving particles generate electric and magnetic field, and that should also act back on the flow. But this back reaction is being ignored by us. This is typically what is called the test particle approximation. You can go beyond that using peak simulations, And there has been talks about peak in pencil coat for quite some time. Philip, Axel, myself, and several other people have talked about it. And I think any time is a good time to start implementing that if we are solving an interesting problem with it. The particles are not relativistic, and we do not make what is called the quasi-static approximation, and I will tell you in one moment what that is. So in some cases, you assume that the particles are so fast that the field actually is not evolving at all in the time scale of the particles. So you keep a snapshot of the field and just use the full particles in that one. We don't do that. The electric field is the velocity cross magnetic field minus eta j. So this altogether is the problem. One new non-dimensional number is what we call the Lorentz number, which is the time scale of the turbulence, tau L, multiplied by the typical frequency of the charged particles, omega c. So let's see a picture of some of our simulations. So you see, these are simulations where we do say, we done say 1, 2, 3, 4, 5, 6 simulations. And in each of the cases, we also force the turbulence as if by an external study. So from the smallest turbulence on the left top to the highest turbulence in the bottom right, you can see in the smallest case, you can see the magnetic field structure quite well. As turbulence gets increased, this structure gets essentially destroyed. So that essentially means that there are lots of small magnetic field lines that connect the internals of this structure. And now we are going to define the reconnection quite specifically. So the reconnection is the rate of change of magnetic flux. So the flux we are looking at is E dot dl. And you can define a reconnection velocity in the following manner. You can choose a contour around this, and you can go up and down that contour. So with this precise reconnection rate, we obtain the following. So this, we look at two things. One is the reconnection rate gamma, and at the same time, we look at the rate magnetic energy is being dissipated, epsilon m. And you see in both of these cases, A corresponds to the case where we have less turbulence, and that is what follows the Sweet-Parker scaling. Whereas as you add more and more turbulence, it goes away from the Sweet-Parker, and you essentially get a reconnection that is independent of the magnetic diffusivity or the Lundquist number.
Dhruva, you have 5 minutes.
Thank you. In such a case, we now put particles in the flow, and lo and behold, what we obtain, we actually obtain a Gaussian distribution of the particles, which basically means is thermal. And as the magnetic field is increased, we get a thermal-like distribution, but the width of the distribution is not set by temperature, but the magnetic field. And you obtain a probability distribution, which, however, remains always Gaussian. The velocity components become anisotropic, but that's not such an important aspect here. The most important aspect here is we look very carefully along the tail of this PDF to see if there is a power law tail or not. There is never a power law tail. Just to assure you, here is a plot of the cumulative distribution of the particle energies as a function of the energies themselves. And it doesn't matter whether we use periodic boundary condition or not. It doesn't change much with the box size, but in the sense that qualitatively, it is always a Gaussian behavior. So whatever we have done, we have always obtained a Gaussian behavior in this problem. But we have always used magnetic fields such that the plasma beta is less than 1. That is, of course, an important aspect of this. So that's what we did then. Now, let me just walk you through what are the various other results in this. One of the earliest studies of this is by Drake in 2006, where you can see they plot a probability distribution of energy just the same that we have plotted. And the claim here is as the plasma beta changes, here you have a power law behavior. So whether you can call it a power law or not is, I think, quite a bit in the eye of the beholder. This is a more recent paper in 2014. And in this paper, they actually look at relativistic cases. And then they start seeing something that maybe you could call a power law. And now let me mention something else to you. There are several groups that have been working on this. And the power laws in peak simulations are not uncommon now. But in almost all the cases, you actually use an extremely high magnetic field. A magnetic field whose strength is larger than the energy that comes from the rest mass of the electrons. Such a case is, of course, important in neutron stars. But it is not very important. It is not at all relevant to the solar problems. So here I am looking at the recent papers which has looked at low plasma beta problems, something that is relevant to the solar problem. So over here below in APJ 2019, the same group, and you may think that maybe there is a power law over here. So one question is the power law non-universal? What does the exponent of the power law depend on? The next question is that what is matter, the relativistic or non-relativistic? How does that matter? The second is you may have a guide field, and it is clear that the guide field actually changes the behavior. This is a more recent paper of the same group as Drake and Guo and several other. And in 2021, they seem to see that there is a power law of an exponent of minus 3.3. So I'm not very sure where things are going. But let me stop here and tell you something else. So you can do a very simple theoretical approach to the problem. You can say that I'm in turbulence, and the only thing that can change the energy of an electron is the electric field. I don't care about the magnetic field. Now, if I look at the correlation of the electric field as the particle moves, so along the particle's trajectory, you expect in a turbulent flow, the electric field will become decorrelated after a certain time. So if you look at times longer than that, you can replace the electric field by a random process. If you do that, then you get an equation where your acceleration is random noise. Now you are familiar with the Brownian motion where velocity is random noise. So when velocity is random noise, displacement square go as t is proportional to time. So when acceleration is random noise, velocity square should be proportional to time. This is exactly what we obtain in our simulation. And this is precisely what will not help us understand the energization process, because there it should be exponential. So I would say the problem is still not closed. And there is a lot of interesting things to be learned by looking at it from a fundamental point of view and trying to match that with the huge amount of data that we are going to get from the Parker Solar Probe and the related radio observations. Thank you.
So thanks, Dhruva, for a very interesting talk. So we have time for 2 quick questions. So anyone, please go ahead. Anyone has any questions? Yeah, Piali, please.
Yeah, hi Dhruva, thank you for giving this talk, and you have another lecture at 10 in 2 hours.
Yes.
And I have a question related to, there's this another group led by Bhargav Vaidya in IIT.
Okay.
I think. So they use this Pluto code, and they have tried to tackle a similar problem where it looks very similar to this paper that you presented here today. So, but they have used relativistic equation, I think. And
yes,
there is some non-Maxwellian distribution, if I remember correctly. So how is that setup different from what you have been doing with the pencil? And I mean, why is it? Is it only because of the non-relativistic the relativistic?
That's a very good question. And that's what I have been trying to understand. As you see, some of these recent papers, that's basically also thank you for asking me to talk about this. I was completely detached from this for quite some time. And because you asked me, I looked into the things again. See, there are relativistic and non-relativistic simulations, and that seems to matter. Certainly the exponent matters. And second is, I think there needs to be care, particular care here. As your electron is getting, firstly, depends on whether you are having electrons or ions, you have a huge difference in time scales. So that time scale, the typical time scale of the electron rotation and the time scale of the turbulence is separated by such a huge amount that it is impossible to do a simulation of realistic Lorentz number. Is that really, is that clear?
Ions and electrons, or?
For ions, definitely for electrons. So you see this Lorentz number, you can see my screen, right? Can you still see my screen?
Yes.
This Lorentz number, the tau times omega c, is actually extremely large in reality. So in our simulations, we use particles that are heavy. So we call them super heavy electrons, okay, which is not realistic. And that is true for almost all simulations. Also peak simulations, they don't use an electron proton plasma. They typically use the electron positron plasma for exactly the same reason. Okay, that's one. Second is, as your electrons gets more and more energized, your Larmor radius becomes larger. And when that becomes comparable to various structures in your flow, for example, it can even become comparable to your box size, then you need to stop your simulation. The other thing is, when the particles move, most people, actually, I think everybody uses periodic boundary condition.
That's not right.
Which I think is somewhat unrealistic. What we did was, our simulations had periodic boundary condition, but whenever an electron reached the boundary of our simulation, we removed it.
And but you don't replace it.
No, we didn't replace it. We just start the simulation again with a lot more of them to collect more statistics. See, because the simulation itself is, the flow is statistically stationary, right? And the probability distribution of the energies that you get are the energies that are collected at the boundaries. Okay, because we were thinking these are the particles that are going to escape.
And those are the ones which will have the highest energies.
Those are the ones that have the highest energies. So, but it may be, and it seems to be, from looking at the various peak simulations, that the resolution matters here very much. Maybe there is a power law hidden in my simulations, which is just cannot be seen because the resolution, the separation of time scales are too small. You see? So looking at this more carefully in higher resolution makes a lot of sense. But at the same time, I would think a peak, there are two things are better ways to go here. One is a peak, and the other is, you see, if we are using test particle approximation, then we should not solve for the charged particle, we should just solve for the guiding center. Right? Because then we don't have this problem of separation of time scale. So it is not difficult to write an equation. Actually, in Arnab's books, there are the equation for the guiding center. So we should actually write, you put that in the pencil code and then solve that. I had this thought about the same time I finished the paper, but we didn't do anything more on that.
Okay. So
I don't think I answered your question. I just raised some more questions.
Yeah.
Yeah, I think we will have some time to discuss in the other lecture.
So Homze has one question, so please go ahead.
Hi, Dhruba. Thanks for the very nice and very clear talk. So I have a question about this Maxwellian result you get.
Yes,
You're using test particles, which means there's no collisions between particles, right?
absolutely.
So but you still get a Maxwellian. So that means something is Maxwellian in the flow, and the particles get equipartition with that.
Not really. Okay, so maybe there is a way to think about it that way. But the way I was thinking was the following. See, the same particles you could also, given that they're in a force field, you can treat each one of them like a Lagrange equation, right?
Mm-hmm.
Do you see what I mean?
Yeah.
Right, and then the turbulence provides the noise in the Lagrange equation.
Mm-hmm. Mm-hmm.
Now, this Lagrange has a corresponding Fokker-Planck.
See. Mm-hmm.
Right, and the Gaussian essentially is a solution of the Fokker-Planck if you assume that there is zero flux.
Mm-hmm.
Right. So essentially, I think this is just saying what you are saying in a different way, that it is reaching equilibrium with something. But the problem is that the equilibrium depends on the magnetic field, not on temperature.
Right, right. But then you see those runs with the power law. So what's the extra ingredient there?
Those who actually see a power law, yes.
That's from those are all from the PIC simulation. So,
those are okay. That's a very good question, because let's look at the slide here. Okay, so 2006, 2014, 2019, all these three are PIC simulation. Okay. Now the latest one, 2019, you see the power law range is not very large. And the 2014 is actually high plasma beta. Okay. So important one is the 2019 one. You see the power law range is not very large. It's about a decade or so. And depends on, it's just a little bit on the eye of the beholder whether it exists or not. But this is the 2021 paper from the same people. I mean, actually from both of this group, the group of Drake and Guo. Okay. And here they're no longer using PIC. Here they use a method they call K-solve, which I haven't figured out yet. But their claim is that the PIC is somewhat insufficient to see this. So I'm in this latest paper in PRL 2021, I'm not sure yet what they're doing.
So we'll go to the next question by Philip.
Yes, I only have a short comment.
Hi, Philip.
Hi, and if we would change from the full PIC description to a guiding center approach description, my experience would tell me that near the reconnection site, I think we would lose the actual non-Maxwellian behavior of the electrons, at least. So
you may be right.
Yeah.
You may be right. Yeah, I think that's a very valid point.
Okay, so